Welcome back. This will be a short video lecture on section 4.3 of the textbook, Determining Statistical Significance. Now I've broken this section up into 5 parts: a review, significance level, statistical decisions, putting it all together, and finally formal versus informal decisions. So let's begin with the review. Now let me describe an experiment for you, and let's calculate the corresponding p-value of the observation. So a study was conducted to compare people's ability to recall memorized information after either the consumption of caffeine or after a brief sleep. A random sample of 24 adults between the ages of 18 and 39 were randomly divided into 2 groups of 12 and verbally given a list of 24 words to memorize. And these groups are pictured here in purple and gold. Now during a break, one of the groups takes a nap for an hour and a half, and the other group is kept awake and then given a caffeine pill an hour prior to testing. The response variable of interest is the number of words participants are able to recall following the break. Now, let's let mu sub s denote the mean number of the 24 words recalled after the nap. In other words, this is a statement about the population. On average, how many words will be recalled within the population after a nap of an hour and a half. Let the parameter mu sub c denote the mean number of the 24 words recalled after consuming caffeine. And likewise, this is a statement about the population. On average, how many words will be recalled within the population after consuming caffeine an hour before the recall test? Now, our null hypothesis is the hypothesis of no effect. The null hypothesis states that there is no difference between mu sub s and mu sub c. So mu sub s minus mu sub c is equal to 0. This is the hypothesis of no effect. The alternative hypothesis, however, is a hypothesis of a one-sided effect, namely that sleep is superior to caffeine for word recall. So the alternative hypothesis says that mu sub s minus mu sub c is in fact positive. That is, mu sub s is greater than mu sub c. Now, the data for this experiment can be viewed in StatKey under Randomization Test for a Difference in Means in the file called Sleep Caffeine Words. And we're going to look at this data set in just a second. But let me point out that the average number of words recalled by the caffeine group, so X bar sub C, is 12.25. Whereas the average number of words recalled by the sleep group, X bar sub S, was 15.25. So this gives us a test statistic of X bar sub S minus X bar sub C, which will be 15.25 minus 12.25, or 3. And so the question for us is, what is the p-value of that observed difference? What is the p-value associated with that observed difference of 3? So let's go to StatKey and take a look at the p-value of this observation. Let's go to StatKey. We're going to be working in the randomization hypothesis tests panel, and in this case we're doing a test for difference in means. And we want to make sure that we load the file sleep caffeine words. Now before we calculate the p-value, let's take a look at the original sample. Now remember, we had a group of 24 volunteers that was split into 2 groups, a sleep group and a caffeine group, and StatKey is labeling the sleep group with the subscripts 1 and the caffeine group with the subscripts 2. Here's the data for the sleep group, and they're colored in this gold color, and here's the data for the caffeine group colored in purple. Now what we want to notice is that for the sleep group, they found 15.25 words on average, and that was out of the 24 words that they were given to memorize. And the caffeine group did a little poorer on this. They found only 12.25 words on average out of the 24 assigned words, and that is an observed difference of 3. Now what we're going to do is simulate the difference X bar sub S minus X bar sub C under the null hypothesis, and we're going to do several thousand simulations and build up the idea of the sampling distribution of that difference under the null hypothesis. So there's 5,000 samples. Now, our p-value is obtained by finding the observation, in this case 3. That was our observed difference. And what we want to know is what proportion of the dots in this dot plot are sitting at or to the right. In other words, in the right tail, starting at or commencing at 3. And we can easily have StatKey do this for us. We're just going to calculate, well, we're going to click on right tail. And we want to make sure that we edit this to 3 so that all of these dots at 3 or beyond are colored in red. And after we do that, we can look up here and see the calculated proportion. What StatKey is telling us is that 0.027, that's the proportion of the dots in the dot plot that are currently colored red, and that's the p-value. So the p-value of our observation is 0.027, or as it is sometimes phrased, 2.7%. So that's our calculation of the p-value associated with this experiment and these samples. Now let's recall the meaning of a p-value. The p-value is the proportion of samples when the null hypothesis is true that would give a statistic as extreme as or more extreme than the observed sample. So a small p-value signifies that something unlikely has occurred. So if we think back to our example that we just studied, this dot plot is giving us a sense of how the value of x bar sub s minus x bar sub c could be distributed under the null hypothesis, right? The vast bulk of these outcomes are hovering close to 0. That's where most of our outcomes, it says most of the time x bar sub s minus x bar sub c will be very close to 0. That's where the mass of this dot plot is. On the other hand, in the one experiment that we conducted, we saw a difference as big as 3, and what we're seeing through this randomization dot plot is that only happens 2.7% of the time. That's a small p-value, and it says that we've just observed something very rare, something rather unlikely. So that's the meaning of the p-value. That's the significance that we attach to the p-value. A small p-value signifies that something unlikely has occurred in our experiment. Now let's think of the challenge posed by a small p-value. Suppose you gather a sample and the p-value of the observed statistic is 0.0267 or 2.67%. I claim that you have two options. Option number 1 is you can continue to not reject H0, but you must also accept that you have just observed something very rare in your sample. The one time you ran your experiment, something that happens only about 3% of the time, something that happens only 3 times in every 100 times that you would run this experiment has just occurred. So that's option number 1. You can continue to not reject H0, but you have to accept that you've just seen something that happens about 3% of the time. That something has just occurred. Option number 2, though, is that you can reject H0 and find favor for the alternative hypothesis H sub A. So let's think of a p-value as a measure of strength of evidence. The smaller the p-value, the stronger the statistical evidence is against the null hypothesis and in support of the alternative hypothesis. So I have this presented in this figure below. When a p-value is small, we should think of the alternative hypothesis as now having more weight. We should feel comfortable rejecting the null hypothesis and lending our favor or support to the alternative hypothesis. So we understand that as the p-value gets smaller, the evidence is growing stronger to support the alternative hypothesis and reject the null hypothesis. But when is p small enough to trigger this response in us? Well, this brings us to the topic of significance levels. The significance level, alpha, for a test of hypotheses is a boundary below which we conclude that a p-value shows statistically significant evidence against the null hypothesis and therefore in support of the alternative hypothesis. So what are some common significance levels? The significance levels of alpha equals 0.05, 5%, or alpha equals 0.01, 1% are typical. Now, if a significance level is not specified, we will assume or we will use alpha equals 0.05 or 5%. That's a very common level of significance. Now, in a proper hypothesis test, the significance level should be set ahead of time. In other words, before any data is collected, any analysis is done, and any p-values are calculated, that significance level should be announced to the world. All right, our experiment is being conducted at the 5% significance level, or our experiment is being conducted at the 1% significance level. The one thing you don't want to do is do all of your analysis, calculate your p-value, and then and only then set your significance level, because you could properly be charged with fudging the data, right? You are waiting to see your p-value so that you can set the significance level to get the conclusion that you want. All right, so to obviate that kind of charge, we should think of the value of alpha as being set ahead of time and that we're conducting our experiment at a 5% significance level, or we're conducting our experiment at a 1% significance level. So the setting of that value of alpha is part of a larger statistical decision-making process. Now let's look at how we make formal statistical decisions. So given a significance level alpha and the p-value from a sample, if the p-value is less than alpha, and that's considered small, then we reject H0. This means that the results are significant and we have convincing evidence in support of the alternative hypothesis H sub A. On the other hand, if the p-value is greater than or equal to alpha, then we do not reject H0. This means that the results are not significant and we do not have convincing evidence in support of the alternative hypothesis. So let's think about the steps that we would follow in conducting a hypothesis test. So a formal hypothesis test includes the following components. Number one, state or acknowledge the significance level alpha. Number two, state the null and alternative hypotheses, defining parameters when necessary. Step three, determine the values of the observed sample statistic. Step four, find the p-value of that observation. Step five, make a decision. We reject H0 in favor of the alternative, or we fail to reject H0. Finally, write a sentence explaining the conclusion of the test in context, indicating whether or not we have found convincing evidence to support the alternative hypothesis. So I'm going to put all of this together and show you how to conduct a couple of hypothesis tests where we run through all 6 of these parts. But before we do that, I want to dig in a little bit on number 6. I want to talk about how we would write a sentence explaining the conclusion of the test in context. So let me show you this in the context of this specific claim. Right? The mean number of finger taps on caffeine is greater than the mean number of finger taps not on caffeine. That's our claim to be tested. We're testing for whether the presence of caffeine in the system will elevate your finger tapping rate. We're looking for evidence that caffeine will elevate your finger tapping rate. So the null hypothesis is the hypothesis of no effect, that the caffeine in your system will have no effect on raising your finger tapping rate. So if we find that the p-value is greater than our significance level, that's considered a large p-value, then there is not sufficient evidence to support the claim that the mean number of finger taps on caffeine is greater than the mean number of finger taps not on caffeine. So that's how we would articulate our conclusion in context in the case that the p-value is greater than or equal to alpha. On the other hand, if the p-value is less than alpha, we are now going to lend our support to the alternative hypothesis, and we will reject the null hypothesis. So in this case, we'll say there is sufficient evidence to support the claim that the mean number of finger taps on caffeine is greater than the mean number of finger taps not on caffeine. All right, so this is how we will articulate our claims, either in the case where the p-value is greater than alpha or the p-value is less than alpha. All I want to point out here is that in both cases, the text in black is the same, right? It's really just the text that we can grab from our claim to be tested. And all we're doing in either case is inserting some different text in red depending upon whether the p-value is greater than alpha or less than alpha. So really what we have to pay attention to are these two clauses in red. There is not sufficient evidence to support the claim that, or there is sufficient evidence to support the claim that. The text in black comes directly from our claim to be tested. All right, let's take a look at putting all of this together in the context of a couple of examples. For our first example, we're going to return to the example we studied at the beginning of this section, right? The question there was, is sleep better than caffeine for word recall? Now, our investigator believes that sleep is better than caffeine, and she wants to demonstrate that. So her claim is that the mean number of words recalled after sleeping is greater than the mean number of words recalled after consuming caffeine. That is the claim to be tested. And what we want to do is conduct a hypothesis test at the 5% significance level. Now, we've done a lot of the work already for this. So what I want us to do is go to the document camera and pull together all of the elements, these 6 steps in conducting a proper hypothesis test at the 5% significance level. So join me at the document camera to fill in these steps. All right, welcome to the document camera. Remember, the claim to be tested here is that the mean number of words recalled after sleeping is greater than the mean number of words recalled after consuming caffeine. We're conducting a hypothesis test at the 5% significance level. So part 1, state or acknowledge the significance level alpha. Well, that's easy. We've been given that alpha is equal to 5%, or we could write that as 0.05. State the null and alternative hypotheses, defining parameters when necessary. So there's a couple of parameters that we want to keep track of here. So these are within the population. So within the population, there will be a mu sub c. We can think of this as the mean words recalled, let's say on caffeine. And then there will be the corresponding mu sub s, and this is the mean words recalled, we could say on sleep. So that's after taking that significant nap. All right, so those are the two parameters that we're working with. So when we state the null and alternative hypothesis, we'll phrase those, of course, in terms of these parameters. So the null hypothesis, which is the hypothesis of no effect, says these are equal to each other. And so we could think of that as mu sub s minus mu sub c equals 0. And the alternative hypothesis is the hypothesis of effect that's consistent with the claim, and that's that mu s is bigger than mu c, or mu s minus mu c is in fact positive. Okay, determine the value of the observed sample statistic. Now, our sample statistic goes along with these parameters. We're going to have an x bar sub s and an x bar sub c within the samples. And what we found is that x bar sub s within the sample group that had the sleep, they found on average 15.25 words, and the sample mean for the caffeine group was less. It was 12.25. And so this gives us our sample statistic, right? This is the x bar sub s minus x bar sub c equaling 3.00. All right. Now what we did this work earlier, so I won't go back to StatKey and replicate this. What we did is we created our randomization dot plot using StatKey, and we found that when we looked at all of the dots that were at or to the right of that observed 3.0, that amounted to a very small fraction of the overall dots. This was like 0.027 or 2.7% of the dots are laying out in that right tail. So the value of the observed sample statistic is 3, and the p-value of that observation was found to be 0.027 or 2.7%. Now we want to make a formal decision concerning the null hypothesis, and this test is being conducted at the 5% significance level or with alpha equals 0.05. And so what we want to do is we want to look to see how do these compare. How does the 0.05 significance level compare to our p-value? And what we're seeing is that our p-value, or 0.027, is falling below the significance level of 0.05. So what is our formal decision concerning H naught going to be? Given this, that the p-value is less than 0.05, our formal decision is going to be we reject H naught, right? We're going to support the alternative hypothesis given this evidence that we found. This small p-value is going to be evidence to reject the null hypothesis and lend our support to the alternative hypothesis. Now, what we want to do is finally express the conclusion in the context. And what we can do is, if we've been very careful about articulating our claim, all we have to do is add a clause in front of that which is consistent with our finding, our rejection of H naught and the lending of our support to the alternative hypothesis. We're going to say something like this: there is sufficient evidence to support the claim that, and all you have to do here now is just take the text that you have in the claim and append it to this clause. So there is sufficient evidence to support the claim that the mean number of words. Now, I'm not going to rewrite this whole thing. You can basically just imagine pulling this down and rewriting it. So you'll fill in all of the remaining part of this claim. So I'll just end it by saying there is sufficient evidence to support the claim that the mean number of words recalled after sleeping is greater than the mean number of words recalled after consuming caffeine. So you get the idea that we can just basically lift our claim and put it in after this initial clause which says there is sufficient evidence to support the claim that. Okay, so that's how we would do a hypothesis test using this 6-step method. All right, let's head back to the class notes and take a look at one more example. For our next example, we want to study the question: is there a correlation between systolic blood pressure and heart rate in ICU admissions? Now, let's turn this into a claim. There is a correlation between systolic blood pressure and heart rate in ICU admissions. Now, we want to test this claim, conduct a hypothesis test at the 5% significance level. Now, what I'm going to do is I'll go to the document camera and we'll work out parts 1 and 2. Then we'll go to stat key and work out parts 3 and 4. And then we'll come back to the document camera and conclude the hypothesis test, finishing with steps 5 and 6. So join me at the document camera to work out the first 2 parts of this problem. All right, welcome to the document camera. Remember, the claim that's being tested here is that there is a correlation between systolic blood pressure and heart rate in ICU admissions, and we're going to conduct a hypothesis test at the 5% significance level. So first, let's state or acknowledge the significance level alpha. And in this case, that's straightforward. We know that alpha is equal to 5% or 0.05. Okay, state the null and alternative hypotheses defining parameters when necessary. Now, there's only one parameter that's evident here in this claim, and that's the correlation between systolic blood pressure, and heart rate and ICU admissions. So let's go off and define rho as the correlation between, let's say, systolic blood pressure and heart rate in ICU admissions. So some people are being admitted to the intensive care unit, and their systolic blood pressure and their heart rate are being determined, and we're going to think about the correlation between those two, and we're going to call that correlation, the correlation that exists within the population, we're going to call that rho. All right, so state the null and alternative hypotheses defining parameters when necessary. So our parameter is rho, that's the parameter we're interested in. Now the null hypothesis is the hypothesis of no effect. We're imagining that these are uncorrelated, so we're going to say that rho is equal to 0. The alternative hypothesis is consistent with this claim that there is in fact a correlation between systolic blood pressure and heart rate in these ICU admissions. Now, the claim is not stating that this correlation is positive or negative. It's just saying that there exists a correlation, leaving open the question of whether that correlation is positive or negative. So the correct way to interpret this alternative hypothesis is that rho is different from 0. And that's going to have an effect on how we calculate the p-value. So we have to keep track of this. This is what's called a two-tailed test. All right, because we'll find evidence for the alternative hypothesis in sample correlations that are negative or sample correlations that are positive. So this is a classic two-tailed test. All right, now we're going to determine the value of the observed statistic and find the p-value of the observation. And we're going to go ahead and do that looking at the data set and doing these calculations using StatKey and its randomization methods. So let's head over to StatKey and do parts 3 and 4. We'll pull those values back into this document, and then we'll finish with 5 and 6 back here at the document camera. All right, so now we're going to work parts 3 and 4. We're going to have to look at the actual data set now. And we're going to work with randomization, hypothesis test for a slope or a correlation. What we're going to want to do is make sure we've got the correct file loaded. So there it is, ICU admissions, systolic blood pressure as a function of heart rate. And here's our original sample. And the thing we really want to pay attention to here is this sample correlation. So we're going to want to make note of that. Within the sample, we're seeing a correlation of negative 0.057. So that's a correlation that's pretty close to 0, but it is slightly negative. And so the question is, how much weight, what's the p-value of this evidence? Now to get that, we're going to create a randomization dot plot of the correlation. So make sure when you are using this panel that you understand that we could be doing a dot plot for the correlation or for the slope of the regression line. So just make sure it's toggled for correlation. And we're just going to generate several thousand samples under the null hypothesis. And we can see this bell-shaped curve emerging. And it's centered, of course, on our null parameter of rho equal to 0. Now all we have to do is find the p-value of this observed statistic. Now we just have to pay attention that this is a two-sided, two-tailed test, so we'll have to calculate the p-value using a left tail and a right tail calculation. So let's begin in the left tail because that corresponds to our observed statistic. We saw an observed correlation of negative 0.057, and we can see that roughly 21.9% of all of the dots land at or to the left of negative 0.057. All right, now we have to tack on a corresponding right tail, and we could double this value, but let's go ahead and have StatKey just calculate the right tail for us as well. So we'll type in right tail and we'll put in 0.057. And so we can see that we're looking at about 20.8% of the dots that are sitting on that side. So we're gonna roughly call the p-value. We don't have to be ultra precise here, especially for a p-value as large as this. Putting these two together, we're going to have a p-value that's on the order of 0.42. So we're going to call the p-value 0.42. So let's head back to the document camera and complete parts 5 and 6 of our analysis. All right, so welcome back to the document camera. Our little foray into StatKey showed us that the correlation that exists within the sample was slightly negative, but still very close to zero, a negative 0.057. And we determined that the p-value using the two-tailed test, the p-value was found to be a rather large 0.42. So this is actually not that unusual. All right, so the p-value is 0.42. Now we need to make a formal decision concerning the null hypothesis. And so what we have to do is compare our p-value with our significance level. And in this case, that's not really a very fair comparison, right? The 0.42 is significantly bigger than the 0.05. So our p-value is far in excess of our significance level. So our formal decision is that we are not going to reject H0. So we do not reject H0. There is no evidence whatsoever in our sample data to support the claim that there is a correlation between systolic blood pressure and heart rate in ICU admissions. That sample correlation is very close to zero, and that doesn't provide us with any evidence in support of this claim. So we do not reject H0. Now we want to express the conclusion in context. So basically we want to go back to the claim and talk about what the evidence is pointing to. And in this case, because of our formal decision, right, there is not sufficient evidence to support the claim that, and here we just have to pull in our clause, right, that there is a correlation and again, I won't write this whole thing out. You're just going to rewrite this text and put it in here. It says that there is a correlation between systolic blood pressure and heart rate in ICU admissions. Right. So the main thing here is that there is not sufficient evidence in our sample data to support that claim. Okay, so that ends our formal hypothesis test. I hope you learned something from that. Let's go back to the class notes. I want to show you one last thing in this section. Now let's end this section with a discussion of formal versus informal decisions. So in a formal decision process, we have a significance level, let's say at 5%, and a p-value of 5.5% is in the range where we do not reject H0, right? And a p-value of 4.5% puts us in the range where we would reject H0 and support the alternative hypothesis. And it is hard to stomach the fact that just a small change in the data set might flip your p-value from 5.5% to 4.5%, and you go from having a conclusion that does not support or does not favor the alternative hypothesis to a conclusion that actually does find significance and finds support for the alternative hypothesis. So what some people would rather do informally is imagine a sliding scale, where as the p-value descends closer and closer to zero, we might have different ways of interpreting that p-value. So for example, for a p-value at 12%, we might find little evidence in support of the alternative hypothesis, right? Whereas for a p-value of 8%, we might find some evidence in support of the alternative hypothesis. At 5%, we might call that moderate evidence in support of the alternative hypothesis. And down around 3%, we might find strong evidence in support of the alternative hypothesis. And then at 1% or less, we might say that the evidence is very strong, right? We have now found a very, very strong evidence in support of the alternative hypothesis. We would gladly reject the null hypothesis and support or favor the alternative hypothesis for a p-value at 1% or less. So this is kind of an informal way of looking at a p-value and assessing its strength. So that's just a quick discussion of the difference between, let's say, a formal decision process at a fixed alpha value and kind of a sliding scale of terms that we could use to indicate the strength of our evidence. Okay, so that brings section 4.3 to conclusion. Until I see you again for section 4.4, take care and be good.